Hello there, and welcome to Earth's history, where the past unfolds slowly, gently, like snow settling on a quiet night. Tonight, we're traveling to a time so strange, so extreme, that it barely seems real. A time when the entire planet, from pole to pole, from the highest mountains to the deepest ocean, turned white with ice. This is the story of Snowball Earth, a frozen world, a planet locked in winter for millions of years. A time when life nearly ended, when the oceans turned solid, when silence fell across continents, and when survival meant waiting in the dark, patient and small, for a thaw that seemed like it might never come. If you've ever watched snow fall and blanket everything in white, transforming the familiar into something quiet and new, you've glimpsed a tiny echo of what happened to Earth. But this was not a winter that lasted months. This was a winter that lasted tens of millions of years. Ice sheets kilometers thick, glaciers covering every continent, the ocean itself, that vast body of water that covers most of our planet, frozen solid. From space, Earth would have looked like a pale blue marble turned white, a snowball hanging in the dark, reflecting the light of a young sun. This is not a story with easy answers. Scientists are still piecing together exactly what happened, exactly how severe it was, exactly how life survived. But what we do know is astonishing, and what we can imagine, standing on the evidence left behind in rocks and ice, is both beautiful and terrifying. Wherever you are right now, I hope you're comfortable. Maybe you're lying in bed with the covers pulled up, feeling the weight of blankets settle around you like snow on branches. Maybe you're watching the evening settle outside your window, the sky dimming from blue to purple to black. Maybe you're in that drowsy space between waking and sleep, where time softens and the mind wanders freely, where thoughts drift like snowflakes, aimless and gentle. If this journey into deep cold and patient survival brings you peace, if it helps you drift toward rest, I'd be grateful if you'd like the video, subscribe to the channel, or share it with someone else who finds comfort in these quiet explorations of Earth's long memory. It helps this little corner of the internet reach others who need a soft place to land at the end of, who seek understanding wrapped in gentle, who want to learn without pressure or hurry. So settle in, let your thoughts slow falling snow, feel your breathing deepen, your muscles relax, your mind quiet, and let's begin. Because roughly 700 million years ago, long before dinosaurs walked, before forests covered the land, before anything you would recognize a complex life exists, the Earth began to freeze, and what followed was one of the most extraordinary chapters in our planet's history. A chapter written in ice and darkness, in patience and endurance, in the quiet persistence of life refusing to surrender. Before we step onto the ice, before we watch the world turn white, we need to see what came before. Because Earth, in the time leading up to the Great Freeze, was not a lifeless rock spinning in the void. It was alive, though not in ways that would feel familiar to us. There were no animals yet, no creatures with eyes to see the sky, no voices to break the silence, no footprints to mark the sand. No one walked these shores. No one swam these seas with purpose or thought. But there was life, abundant, patient, ancient life, life that had been perfecting itself for billions of years, life that had transformed the planet, life that had created the very oxygen we would one day breathe. This was the Neoproterozoic era, a stretch of time spanning from about 1 billion years ago to 541 million years ago. The name itself sounds distant, foreign, a label for a world so removed from ours that it might as well be another planet. And in many ways, it was. We're focusing on the later part of this era, around 750 to 635 million years ago, when snowball Earth events occurred. During this time, Earth's continents were not arranged the way they are today. There was no Atlantic Ocean splitting the Americas from Europe and Africa, no Pacific stretching its vast emptiness between Asia and the Americas, no Indian Ocean, no Mediterranean, no familiar shapes on any map. Instead, a supercontinent called Rodinia had recently broken apart, its fragments drifting slowly across the globe, carried by the endless, patient movement of tectonic plates. Rodinia itself had been assembled from even older continental pieces, gathered together over hundreds of millions of years by the slow collision of landmass. For a time, perhaps 200 million years, it had stood as one. But continents never rest. The same forces that brought Rodinia together eventually pulled it apart. Rifts opened, new ocean basins formed. The fragments drifted away from each other, spreading across the globe like pieces of a puzzle scattered across a table. The oceans were vast and shallow in many places, their waters warm near the equator, cooler toward the poles. Continental shelves extended far from shore, creating broad platforms where sunlight could penetrate all the way to the bottom. These These shallow seas were the most fertile regions of the planet, the places where life concentrated and thrived. And in those oceans, life thrived in forms that seem almost alien to us now. The most visible signs of life were stromatolite, layered mounds built by colonies of cyanobacteria. These microbes, descendants of the organisms that had first released oxygen into the atmosphere billions of years earlier, were Earth's master engineer. They formed sticky mats on the seafloor, their surfaces covered in a slime that trapped sediment. Sediment would settle on the mat, and the bacteria would grow upward through it, creating layer after layer, like living stone. Over time, these layers hardened into rock, forming domed structures that could grow meters tall, some reaching heights taller than a person. They grew slowly, perhaps a millimeter per year, each layer marking the passing of seasons, the rhythm of tides, the patient accumulation of time. If you could have walked along a shallow coastline in this ancient world, wading into water that lapped at your knees, you would have seen these stromatolites dotting the seafloor like strange stone mushrooms. Some were domed, smooth and rounded. Others were more columnar, rising in pillars from the bottom. Still others formed in branching shapes, like petrified trees made of living slime and sediment. The water would have been clear, perhaps tinged greenish by the algae and bacteria floating in it, casting dancing shadows on the sandy bottom. There would have been no fish darting between the rocks, no crabs scuttling across the sand, no seabirds calling overhead, just the lap of waves, the whisper of wind, and beneath the surface, the slow, silent work of microbes building their mineral towers, grain by grain, layer by layer, year after patient year. In deeper waters, other forms of life drifted. Simple algae, multicellular, but without the complexity of plant, without roots or leaves or flowers. They were just clusters of cells, green with chlorophyll, floating with the currents or anchored lightly to the bottom. Perhaps early sponges existed too, soft-bodied and sessile, anchored to the seafloor, their porous bodies filtering nutrients from the passing current. They didn't move, didn't hunt, didn't flee. They simply filtered, pulling tiny particles of food from the water, growing slowly in the dim light of the deep. The fossil record from this time is sparse, frustratingly so. Soft-bodied organisms rarely fossilize. They decay, they're eaten, they're crushed and scattered. Only under the most unusual circumstances, when burial is rapid and conditions just right, do they leave impressions in stone. But we know that by the late Proterozoic, life had begun to experiment with larger, more complex forms. Cells had learned to stick together, to specialize, to divide labor. Some cells became good at capturing light. Others became good at structure, forming the scaffolding that held colonies together. Still others specialized in reproduction, ensuring the colony could spread and persist. It was the beginning of something new, though no one could have predicted how far it would go. These were not yet animal, not in the sense we understand them. They had no nervous system, no brain, no eyes or mouths or limb. But they were more than just individual cells. They were communities, working together, and in that cooperation lay the seeds of all the complexity that would follow. On land, there was almost nothing. No plants, no animals, no soil as we know it. Soil is created by the action of living things, roots breaking rock, organisms dying and decomposing, their bodies enriching the dirt. Without life on land, there was no soil, just bare rock, weathered by wind and rain, slowly breaking down into sand and dust. Rivers carved valleys, but their banks were lifeless, just stone and gravel. Mountains rose and eroded, their peaks scraped by wind, their flanks carved by water. Volcanoes erupted, sending ash into the sky, painting the landscape in shades of gray and black. The continents were stages, waiting for actors that had not yet evolved. Empty theaters where the drama of terrestrial life would one day unfold, but not yet. Not for hundreds of millions of years still. The atmosphere was different too. Oxygen levels were lower than today, perhaps around 10 to 15% compared to our current 21%. This might not sound like a huge difference, but it mattered. Lower oxygen means less energy available for metabolism, which means organisms can't grow as large or move as quickly. It means that the insects of this time, if any existed, were small. It means that fires, if they started, burned less fiercely. The world was, in a sense, calmer, quieter, slower. There was more carbon dioxide in the atmosphere than today, though not as much as in Earth's earliest days, when the planet was still young and volcanic. The sky would have been blue, but perhaps a slightly different shade, with a faint haze on the horizon, and the climate, overall, was moderate. Not too hot, not too cold. The equator was warm, the poles were cool, and in between stretched a gradient of comfortable temperatures. The planet was in balance, or so it seemed. The sun warmed the surface, greenhouse gases trapped heat, weathering removed CO2, volcanoes replenished it, life absorbed and released gases, cycling carbon and oxygen through the biosphere. Everything was connected, everything in motion, everything balanced on the edge of stability. But that balance was delicate, more delicate than it seemed, and it was about to break. The mechanisms that triggered Snowball Earth are complex, layered, interconnected. Scientists are still debating the details, running computer models, analyzing rock, trying to piece together exactly how the planet tipped from temperate to frozen. But the basic story goes something like this. Earth's climate is regulated by a delicate dance between incoming sunlight and outgoing heat, between greenhouse gases that trap warmth and processes that remove them. It's a system of feedback, positive and negative, that keep the planet within a habitable range. One of the most important of these processes is weathering. When rain falls, it dissolves carbon dioxide from the air, forming a weak acid, carbonic acid. This is the same acid that gives soda its fizz, but in rainwater, it's very dilute. This acidic rainwater reacts with rock, particularly silicate rock like granite and basalt, breaking them down chemically. The reaction dissolves minerals from the rock, releasing calcium, magnesium, and other ions into the water. These ions are washed into rivers, carried downstream, and eventually reach the ocean. In the ocean, organisms, mostly microscopic algae and bacteria, use these minerals along with carbon dioxide dissolved in the water to build shells and skeletons. The chemical formula for this is simple but profound. Calcium plus carbonate equals calcium carbonate limestone. When these organisms die, their shells and skeletons sink to the seafloor and are buried under layers of sediment. Over millions of years, they turn into rock, thick beds of limestone that lock away the carbon. This process, called the carbonate-silicate cycle, acts like a thermostat for the planet, a planetary feedback system operating on geological timescales. If the Earth gets too warm, more water evaporates from the oceans. More evaporation means more rain. More rain means more weathering. More weathering means more CO2 is removed from the atmosphere and locked away in limestone. And with less CO2 trapping heat, the planet cools down. Conversely, if the Earth gets too cold, less water evaporates, less rain falls, weathering slows, but volcanoes continue to erupt, releasing CO2 that isn't being removed. The CO2 accumulates in the atmosphere, trapping more heat, and the planet warms up again. It's an elegant system, a negative feedback that has kept Earth's climate relatively stable for billions of years. But this system has a weakness, a breaking point. If the continents drift into certain configurations, if weathering becomes too efficient, if CO2 levels drop too low, the cooling can spiral out of control. The thermostat can break, and that's what may have happened in the Neoproterozoic. As Rodinia broke apart, new coastlines were created. Coastlines are where weathering happens most efficiently. Rain falls on land, runs over fresh rock, and carries dissolved minerals to the sea. When you have more coastline, you have more weathering. The fragments of the supercontinent, freed from their ancient bonds, began to drift slowly across the globe, and many of them drifted toward the equator, where rain was abundant, where tropical storms dumped water on the land year-round. Weathering accelerated. More rock was exposed. More rain fell. More CO2 was pulled from the atmosphere. And as CO2 declined, so did the greenhouse effect. The planet's blanket grew thinner. More heat escaped into space. Temperatures fell. At first, this cooling was gradual, almost imperceptible. Perhaps over thousands of years, the average temperature dropped by a degree, then another. Ice began to form at high latitude, in the polar regions, where the sun's rays strike at the shallowest angle and deliver the least heat. Glaciers spread across the land, grinding down from mountain peaks, flowing like rivers of ice toward the sea. Snow accumulated year after year, compacting into ice under its own weight, building up layer upon layer. And this is where the feedback loop began, where the system started to run away with itself. Ice is white, and white surfaces reflect sunlight back into space, a property called albedo. Fresh. Snow can reflect up to 90% of the sunlight that hits it. Water, by contrast, absorbs most of the sunlight. So when ice forms, the amount of heat the planet absorbs drops dramatically. The more ice there was, the more sunlight was reflected, and the less heat Earth absorbed. As the planet cooled, more ice formed, and as more ice formed, the planet cooled further. Each step reinforced the next, amplifying the change, pushing the system toward an extreme. This positive feedback, this runaway cooling, is the engine of Snowball Earth. Once it starts, it's very hard to stop. Ice spreads from the poles toward the equator, advancing year by year, decade by decade, century by century. Sea ice forms on the ocean surface, starting at high latitudes and advancing toward the tropics. And as the ice advances, the albedo increases, the cooling accelerates, and the ice spreads faster. It's a race, a cascade, a tipping point crossed and impossible to uncross. At some point, a threshold is crossed. The ice reaches a critical latitude, perhaps around 30 degrees, roughly where the subtropics are today. And then, suddenly, catastrophically, the entire planet freezes. Ocean ice spreads to the equator. Continental glaciers merge into vast ice sheets. The world turns white. This is what we call snowball Earth, a planet transformed, a world locked in ice. The descent into ice did not happen overnight. It took time, perhaps thousands of years, for the planet to transition from a world with polar ice caps to a world completely frozen. But on geological timescales, it was rapid, almost instantaneous, a blink in deep time. And once it began, there was no stopping. The feedback had taken over, the system had tipped, and Earth was committed to the freeze. Imagine you could watch this process unfold, time-lapse, across centuries and millennia. Imagine standing in one spot, somehow immortal, watching the world change around you. In the first years, you would see snow falling more heavily at the poles, winters growing longer, summers growing shorter and cooler, glaciers advancing, calving icebergs into the sea with thunderous cracks, sea ice spreading outward from the Arctic and Antarctic, covering more of the ocean each winter, retreating less each summer. The climate growing colder year after year. The change subtle at first, but accelerating. Within decades, the changes would be dramatic. Ice sheets covering the northern continent, extending south like slow-motion avalanche. Regions that had been green with microbial life now buried under meters, then tens of meters, then hundreds of meters of ice. The ocean freezing over in higher latitudes, the surface hardening into a solid lid. Coastlines transform. What was once water, now a solid plain of white stretching to the horizon. The few simple organisms that lived there, though few and simple they were, would be driven away or buried or frozen into dormancy. Within centuries, the ice would reach the mid-latitude region that had once been temperate, where liquid water flowed year-round, where stromatolites built their patient towers in shallow seas, would freeze. Rivers would stop flowing, their surfaces hardening into ice roads. Lakes would freeze to their bottoms, entombing whatever lived there, and still the cold would advance, relentless, unstoppable, driven by its own momentum. Within millennia, the equator itself would feel the chill. Snow falling in regions that had never known winter, regions where the sun had always shone warm and steady. The last open water, the last refuge of warmth, slowly shrinking. Animals, if any existed with the ability to move, would have nowhere left to go. The whole planet was becoming uninhabitable. And then, one year, perhaps after 10,000 years of steady cooling, it would freeze over. The last patch of open ocean turning solid, the last ripple stilling, the last wave frozen mid-crest, and Earth would be white from pole to pole, a snowball hanging in space, silent and still. This happened not once, but at least twice, possibly more. The first event, called the Sturtian glaciation, began around 717 million years ago and lasted for approximately 57 million years. Yes, you read that correctly. 57 million years. A span of time so long that it dwarfs all of human history. The pyramids of Egypt, those monuments we consider ancient, were built less than 5,000 years ago. They are babies compared to the Sturtian freeze. Modern humans, Homo sapiens, have existed for perhaps 300,000 years. That's less than 1% of the duration of the Sturtian glaciation. 57 million years is almost incomprehensible. It's a time span during which continents can drift thousands of kilometers. Mountain ranges can rise from ocean floors and erode back to plains. Stars can form from clouds of gas and begin their long burning. Entire lineages of life can evolve, flourish, and go extinct without ever experiencing anything but ice. The second event, the Marinoan glaciation, occurred around 650 million years ago and lasted for about 15 million years. Still an enormous span of time, longer than the entirety of human existence by far, but shorter than the first. Both of these freezes left marks in the rock record that we can still read today, evidence written in stone that speaks across hundreds of millions of years. But what would it have been like to stand on Earth during one of these snowball events? Not to study it from afar, not to read about it in paper or see it in diagrams, but to be there, to feel it, to experience the cold and the silence and the vastness of the ice. Let's step onto that frozen world and see. Let's imagine ourselves there, standing on the surface of Snowball Earth, witnesses to a planet in its coldest, strangest, most extreme state. You're standing on a glacier. But this is not a glacier like those that exist today in Greenland or Antarctica, impressive as those are. This is something far larger, far thicker, far more absolute. The ground beneath your feet is solid ice, not the thin layer of ice you might walk on during winter, not even the meter-thick ice that forms on northern lakes, but ice that extends down for hundreds, perhaps thousands of meters. Beneath this ice is rock, the continent itself, buried and hidden, separated from the sun and air by a barrier of frozen water so thick that it would take years to drill through it, even with modern equipment. The ice is not smooth. Wind and the slow movement of the glacier have carved it into ridges and valleys. Pressure cracks where the ice buckles under its own immense weight, and towering seracs, columns of ice that rise like frozen monuments, some as tall as buildings. The surface is textured, rough in places, polished, smooth in others, where the wind has scoured it for millennia. There are no colors except white and pale blue. The ice absorbs red light and reflects blue, giving it a cold, ethereal glow in the dim sunlight. The temperature is brutally cold. In the interior of the continent, far from any ocean, far from any source of warmth, temperatures may have dropped to 50 degrees Celsius or lower. That's colder than the coldest nights in Antarctica today. That's cold enough to freeze carbon dioxide out of the air, cold enough to make metal brittle, cold enough to kill any unprotected organism in minutes. Even at the equator, where the sun shines most directly, where solar radiation is strongest, the ice reflects so much sunlight that temperatures remain well below freezing year-round. There is no summer here, no spring or autumn, no seasons at all in any meaningful sense. Just an endless winter, a perpetual cold that has no memory of warmth, no hope of thaw. The wind is constant, unrelenting. It sweeps across the ice without obstruction, howling and shrieking, a sound that never stops, that becomes the background of existence. It carries tiny crystals of ice, fragments broken from the surface, that sting any exposed skin like needles. These ice crystals scour the surface, polishing it, reshaping it, grain by grain. There are no trees to block the wind, no buildings to shelter behind, no valleys deep enough to escape it, just ice and wind and cold, stretching to every horizon. The sky above is a pale, washed-out blue during the day, the color bleached by the brightness of the endless ice below. The sun is visible, a dim disk in the sky, but it seems distant, its warmth stolen before it ever reaches. Ice crystals suspended in the air create optical effects, strange halos and sundogs, rings of light, and phantom suns that shift and shimmer. At night, the stars are brilliantly clear, unobscured by clouds or moisture or dust. The Milky Way stretches overhead in a river of light so bright you could read by if there were anything to read. Auroras dance near the pole, curtains of green and red flickering against the darkness, caused by solar particles interacting with the thin atmosphere. They're beautiful, hauntingly so, a display of color in a world stripped of it. But there is no sound except the wind, no birds crying, no rustle of leaves, because there are no leaves, no trees, no plants of any kind, no splash of water, because all water is locked in ice. No crack of branches, no buzz of insects, no calls of animals, just the wind, that endless wind, and the occasional crack of ice shifting under its own immense weight, a sound like distant thunder that rolls across the frozen plain. It is a world of profound silence, silence made more profound by the vastness, by the knowledge that this silence extends across the entire planet, from pole to pole, from mountain to plain, unbroken and absolute. If you could somehow travel to the ocean, perhaps walking for weeks across the frozen land, descending from the continents onto what was once the seafloor, you would find it frozen as well. Sea ice covers the surface, perhaps a kilometer thick in some places, a lid of frozen water sealing the ocean from the sky. The surface is rougher here, pushed up into pressure ridges, where currents below once caused the ice to buckle and fold. In some places, the ice is milky white, filled with tiny air bubbles trapped during freezing. In others, it's crystal clear, a window into the darkness below. Beneath this lid, the ocean still exists. It's dark down there, darker than the deepest cave, because no light penetrates through a kilometer of ice. It's cold, just barely above freezing, hovering at the point where salt water remains liquid. And it's still, unmoving, except for the slowest currents, driven by temperature and salinity differences. It's a trapped ocean, cut off from the sun, from the atmosphere, from the cycles that once sustained it. No oxygen enters from above. No carbon dioxide escapes. No sunlight penetrates to fuel photosynthesis. It is waiting in darkness, a liquid world beneath a frozen shell, silent and patient. And in this darkness, in this cold, in this isolation, life clung on, somehow, against all odds. In refuges, we're still trying to understand. This is perhaps the most astonishing part of the Snowball Earth story, the part that transforms it from a tale of planetary catastrophe into a story of survival against impossible odds. Earth froze solid, or nearly so, for tens of millions of years. Temperatures plummeted to levels that would kill most modern organisms in minutes. The sun was blocked by ice and clouds. Photosynthesis, the process that had sustained most life for billions of years, became impossible on the surface, impossible in the shallow seas where most life lived. The world seemed to have become uninhabitable, a dead planet, a frozen tomb, and yet life did not end. Somehow, somewhere, in pockets and refuges scattered across the frozen world, it found ways to survive. It didn't thrive. It didn't evolve much, or spread, or diversify. But it waited. It endured. It held on to existence by the thinnest of threads, patient beyond measure, stubborn beyond belief. But where? Where could life possibly survive in such conditions? And how? Scientists have proposed several possibilities, several refuges where life might have endured the long freeze. None of them are certain. We can't go back in time and see what actually happened. Can't observe the survival strategies of organisms that lived and died hundreds of millions of years ago. But we can make educated guesses based on what we know about life today, about Earth's system, and about the conditions that must have existed during Snowball Earth. And those guesses, those hypotheses, paint a picture of life pushed to its absolute limit, surviving in ways and places that seem almost miraculous. The first and perhaps most likely refuge is deep in the ocean, at hydrothermal vents. These are cracks in the seafloor where hot, mineral-rich water wells up from the Earth's interior, driven by heat from the mantle below. Today, these vents support entire ecosystems of bacteria, tube worms, clams, and shrimp, all of which survive without any sunlight at all. They rely on chemosynthesis, a process where bacteria use chemicals like hydrogen sulfide, which would be toxic to most organisms, to generate energy. It's like photosynthesis, but instead of using sunlight, these bacteria harvest energy from chemical bonds. They're the base of the food chain at vents, and everything else lives off. During Snowball Earth, hydrothermal vents would have continued to operate. The Earth's interior doesn't care if the surface is frozen. Heat from the mantle still rises, inexorably, driven by radioactive decay and the residual heat from the planet's formation. Tectonic plates still move, though perhaps more slowly under the weight of ice. And where those plates spread apart at mid-ocean ridges, or where they subduct at plate boundary, creating fractures and weaknesses in the crust, hot water still flows up from below, carrying minerals and heat. In these warm oases, scattered across the frozen ocean floor, bacteria could have survived. Perhaps not thrived in the sense of spreading and diversifying. Perhaps not evolved much during the freeze, but survived, endured, persisted, clinging to the rocks around the vents, feeding on the chemicals in the water, reproducing slowly in the warmth, maintaining populations that might have numbered in the billions, but were insignificant compared to the vastness of the frozen world above. They were cut off from the rest of the planet, isolated in pockets of heat in a frozen ocean, islands of warmth in an ice age ocean. But they endured, generation after generation, waiting for conditions to change, though they had no knowledge that change would ever come. Another possible refuge is beneath the ice itself, in the thin layer of liquid water that might have existed between the ice and the ocean below. The ice on the ocean surface would have been thick, perhaps hundreds of meters in some place, a massive lid pressing down on the water. But ice is not completely opaque, not perfectly black. Light can penetrate, especially if the ice is relatively clear and free of debris and air bubbles. Think of glacial ice, which is often a beautiful clear blue, transparent enough to see through. In some areas of Snowball Earth, particularly near the equator where the sun shines most directly, where its rays strike the ice at the steepest angle and deliver the most energy, enough light might have filtered through the ice to allow photosynthesis to occur in the water immediately below. This would have been dim, difficult photosynthesis, nothing like the bright sunlit conditions in which most plants and algae thrive today. The light reaching the water would have been faint, a twilight glow at best, perhaps only 1% or even less of the light that reaches the surface. Colors would have been muted, shifted toward the blue end of the spectrum because ice absorbs red light. But some algae and cyanobacteria might have adapted to these low light conditions, evolving or expressing genes that allowed them to capture every available photon, eking out a slow, minimal existence in the dim blue glow. Growth would have been sluggish, barely faster than the cells died. Populations would have been small, sparse, scattered, but it might have been enough to maintain a presence, to keep the spark of photosynthetic life alive through the long freeze. Today, we see analogs of this in places like Lake Vostok in Antarctica, a massive lake buried beneath nearly 4 kilometers of ice. Despite the crushing weight and the near total darkness, despite temperatures well below freezing, kept liquid only by the pressure of the ice above, microbes live in that lake, adapted to conditions that seem impossibly harsh by surface standard. If life can survive there now, thriving in isolation beneath ice, perhaps it survived beneath the ice of snowball Earth as well, waiting in the darkness for the return of light. A third possibility involves volcanic islands, places where the heat of the Earth's interior breaks through to the surface, even during the deepest freeze. Even during snowball Earth, volcanoes would have continued to erupt. Magma doesn't stop rising just because the surface is frozen. It pushes upward, driven by buoyancy and pressure, finding pathways through the crust. When it erupted, the heat from the lava and the geothermal activity around the volcano would have melted the ice locally, creating pools of liquid water, perhaps even small lakes, oases of warmth in the frozen wasteland. These pools might have been temporary, refreezing once the eruption ceased and the heat dissipated. But for a time, days or weeks or months or even years, depending on the size of the eruption, they would have provided pockets of warmth where life could gather. Bacteria and algae, frozen in the ice or drifting dormant in the ocean below, might have been carried by melt currents to these volcanic oases. There, in the warm water heated by geothermal springs, they could have become active again, their metabolism restarting, reproducing, and spreading before the cold returned. It would have been a precarious existence, a cycle of freezing and thawing, dormancy and brief flourishing, death and resurgence. But life is nothing if not resilient, nothing if not opportunistic. Wherever liquid water existed, life would have tried to colonize it, to take advantage of every brief opportunity. And finally, there's the possibility of something called cryoconite holes. The name sounds technical, almost mystical, but the phenomenon is simple and beautiful. These are small depressions in the surface of glaciers where dark particles, dust, volcanic ash, or even microbes themselves absorb sunlight and melt the ice around them. Dark surfaces absorb heat, while light surfaces reflect it. So a speck of dust on bright white ice will warm up, melt the ice beneath and around it, and sink into a small pocket. The result is a tiny pool of liquid water, often just centimeters across and a few centimeters deep, sitting in a depression in the ice. The water in these pools can be surprisingly warm on sunny days, reaching temperatures well above freezing, even when the surrounding air is cold. These pools exist on glaciers today, and they're teeming with life. Algae, bacteria, even tiny invertebrates live in these miniature ecosystems, these specks of liquid water in a world of ice. They're isolated from each other, each pool its own little world, but together they represent a strategy for survival in extreme condition. On snowball Earth, cryoconite holes might have formed wherever dark material accumulated on the ice surface. Volcanic ash falling from eruption, dust blown across the ice by the constant wind, meteorites burning up in the atmosphere and sprinkling their debris across the surface. Even concentrations of microbes themselves, dead and frozen, darkening the ice enough to create a feedback. And in those tiny pools, scattered across the vast frozen surface, like islands in an ocean of ice, life could have survived. It would have been a fragile existence, dependent on the brief warmth of summer sunlight at the equator, where the sun never set below the horizon for months at a time, vulnerable to being buried by snow, or blown away by wind, or refrozen if clouds blocked the sun. But it's another possible refuge, another way life could have held on, another testament to the incredible resilience and adaptability of living things. All of these scenarios, these hypotheses about survival, share one thing in common. Life would have been reduced to its simplest, hardiest form. Complex organisms, if they existed at all before the freeze, would almost certainly have been wiped out. They would have had nowhere to hide, no way to survive the cold and darkness. Only the smallest, toughest microbes would have survived. Organisms that could enter dormancy, that could slow their metabolism to almost nothing, that could repair damage to their DNA and proteins caused by freezing, that could wait, patient beyond human comprehension, for conditions to improve. Bacteria and archaea, single-celled organisms without nuclei, masters of survival in extreme conditions. Single-celled algae and cyanobacteria, photosynthetic organisms that could shut down when light disappeared and restart when it returned. Perhaps simple multicellular organisms, early experiments in cooperation between cells, organisms capable of forming dormant spores or cysts, protective shells that could survive freezing and desiccation and crushing pressure, waiting out the hard times in a state of suspended animation. And for most of these survivors, survival meant waiting, not actively living in any meaningful sense, not growing or reproducing much, not spreading or evolving or adapting, but simply enduring. Metabolism slowed to a crawl, to the bare minimum needed to maintain basic function. Cells entered states of dormancy. Their internal processes nearly shut down. DNA coiled tightly. Proteins folded into protective configuration. Membranes reinforced against the stress of freezing. Just enough activity to maintain the integrity of the cell and repair damage caused by ice crystals forming in and around them. Time, for them, stretched out. Days blurred into years blurred into millennia, millennia into epoch, and still the ice remained, and still they waited. This is perhaps the hardest thing for us to grasp about Snowball Earth, the thing that defies our intuition and imagination, the sheer duration of it, the incomprehensible length of time during which the planet remained frozen. We're used to thinking of disasters as short-term events, things that happen and then end. A hurricane strikes, and within weeks, cleanup begins. A wildfire burns, and within months, the first green shoots emerge. A volcano erupts, and within years or decades, life begins to return to the slope. Even the asteroid impact that killed the dinosaurs, as catastrophic as it was, led to recovery within a few million years. That seems like a long time to us, but in geological terms, it's rapid. But Snowball Earth lasted for tens of millions of years, 57 million years for the Sturtian, 15 million years for the Marinoan. These are time spans during which entire mountain ranges, the Himalayas, the Andes, the Rockies, could rise from sea level to their full height, and then erode halfway back down again. Continents could drift thousands of kilometers, opening new oceans, closing old ones, reshaping the map of the world beyond recognition. Stars in the Milky Way could complete entire orbits around the galactic center. Stars could be born from clouds of gas, burn through their fuel, and die in supernovae, scattering their atoms back into space to form new stars. And through it all, through this incomprehensible stretch of time, the ice remained, unbroken, unchanging, silent. The sun rose and set, rose, and set billions of times. The moon orbited the Earth, pulling tides that moved beneath the ice, invisible and unfelt. Volcanoes erupted, painting the white landscape with black ash. Meteorites fell from space, punching holes in the ice, creating brief flashes of heat that vanished almost instantly. But nothing changed the fundamental state of the planet. It was frozen. It remained frozen. And it seemed as though it would remain frozen forever. But nothing lasts forever. Not even ice. Not even a freeze that has endured for 50 million years. Because while the surface of Earth was locked in an endless winter, while the continents were buried and the oceans sealed, while life clung to survival in scattered refugees, the planet's interior remained active, hot, restless, indifferent to the cold above. Deep beneath the ice, far below the frozen ocean, beneath the crust itself, in the mantle, that thick layer of semi-solid rock that makes up most of Earth's volume, heat continued to build. This heat comes from two sources. Some of it is left over from the planet's formation, from the violent collisions that created Earth 4.5 billion years ago. When rocks collide at cosmic speed, their kinetic energy converts to heat, and that heat is trapped inside the growing planet. It takes billions of years to radiate away. Some of the heat comes from radioactive decay, from unstable isotopes of uranium, thorium, and potassium scattered through the rock, slowly breaking down, releasing energy as they transform into more stable elements. This process has been going on since Earth formed, and it will continue for billions of years into the future. This heat drives convection currents in the mantle, slow upwellings of hot rock, and downwellings of cooler rock, like a pot of thick porridge simmering on a stove. The rock doesn't melt, not quite, but it flows over geological time, plastic and malleable under the immense pressure and temperature. These convection currents carry heat from the interior toward the surface, and they drive the movement of tectonic plates. The plates ride on top of the convecting mantle, carried along like logs floating on water, spreading apart at mid-ocean ridges, colliding at subduction zone, grinding past each other at transform fault. And even during Snowball Earth, even with the surface frozen solid, even with ice pressing down on the crust, with the weight of kilometers of of accumulated snow, the plates continued their slow, patient dance. They moved perhaps more slowly, slowed by the weight of ice, by the changed distribution of mass on the surface, but they moved. Continents drifted, ocean floors spread, and where the crust was thin, where magma found pathways to the surface, where the upwelling mantle came close to breaking through, volcanoes erupted. They erupted under the ice, the lava melting through it, sending plumes of steam and ash into the frozen sky. They erupted on the seafloor, hidden beneath the frozen ocean, their heat dissipating into the cold water, their lava cooling instantly into pillows of glass-crusted rock. They erupted on the continent, building new mountains of cooled lava, painting the white landscape with black and red stone, temporary islands of warmth in an ocean of cold. And more importantly than the lava, more importantly than the visible eruption, these volcanoes released gas. Carbon dioxide, mostly, along with water vapor, sulfur compounds like sulfur dioxide, nitrogen, and other volatile. These gases had been dissolved in the magma deep below, held in solution by pressure. But when the magma rose and the pressure decreased, the gases came out of solution, bubbling up like carbon dioxide, fizzing out of a shaken soda bottle. They vented into the atmosphere through volcanic craters, through fumaroles and hot springs, through cracks in the crust. In normal times, this volcanic CO2 would be removed from the atmosphere by weathering and by photosynthetic organisms. Plants and algae would absorb it, incorporating the carbon into their tissues. Rain would dissolve it, washing it into the ocean, where it would eventually be locked away in limestone. The carbonate-silicate cycle, that planetary thermostat, would regulate it, keeping CO2 levels within a reasonable range. But Snowball Earth was not normal time. The regulatory systems had failed. The thermostat was broken. Weathering had nearly stopped. Weathering requires liquid water, rain falling on exposed rock, dissolving minerals, washing them away. But with the oceans frozen, the water cycle was broken. Water couldn't evaporate from the ocean surface because it was sealed under ice. No evaporation meant no cloud. No clouds meant no rain, except perhaps the tiniest amount from ice sublimating directly into vapor in the thin air above the glacier. Without rain, weathering slowed to a crawl. The ice itself could weather slowly, reacting with the CO2 in the air, frost weathering, breaking down exposed rock. But these processes are much slower than liquid water weathering. They couldn't keep up with volcanic emissions. And photosynthesis, which removes CO2 from the atmosphere and releases oxygen, had been drastically reduced. Most photosynthetic life was either dead, frozen, or dormant. The little that survived in isolated pockets, around hydrothermal vents, beneath the ice, in volcanic pools, in cryoconite holes, was not nearly enough to make any significant dent in atmospheric CO2 levels. The balance was broken. CO2 was being added by volcanoes, but it wasn't being removed at anywhere near the same rate. So the volcanic CO2 accumulated, year after year, century after century, millennium after millennium, eruption after eruption. The concentration of carbon dioxide in the atmosphere increased. At first, the change was small, imperceptible. One eruption might add a few parts per million. 10 eruptions might add 100. It was a drop in the ocean, insignificant against the vastness of the atmosphere. But over millions of years, those small additions became significant. CO2 levels rose from hundreds of parts per million, the level they might have been before the freeze, to thousands, and then tens of thousands, and then perhaps even higher. Some estimates, based on computer models and calculations of volcanic output and weathering rates, suggest that by the end of a snowball Earth event, CO2 concentrations might have reached 100,000 parts per million or more. That's hundreds of times higher than modern levels, which are around 420 parts per million. It's even higher than the levels during some of Earth's hottest periods in the past. The atmosphere would have been thick with carbon dioxide, heavy, dense, a blanket wrapping the planet. Carbon dioxide is a greenhouse gas. It's transparent to visible light, the kind of light that comes from the sun, so sunlight passes through it easily and strikes the surface. But it's opaque to infrared radiation, the kind of heat radiation that the Earth emits back into space. So CO2 in the atmosphere acts like a one-way mirror. Light comes in, but heat can't get out. It's trapped, warming the atmosphere and surface. The more CO2 there is, the stronger the greenhouse effect, the more heat is trapped. And as the concentration of CO2 increased over millions of years, so did its warming effect. At first, this warming was imperceptible, completely overwhelmed by the ice albedo feedback. The ice reflected so much sunlight, 80–90% of it, that even with elevated CO2, even with a strengthening greenhouse effect, temperatures remained well below freezing. The planet stayed locked in ice. The cold was too strong, the feedback too powerful, but slowly, so slowly that it would be invisible on human timescale, imperceptibly on the scale of centuries or even millennia, but inexorably on the scale of millions of years. The balance shifted. The greenhouse effect strengthened. The atmosphere held more and more heat, and the surface temperature, though still far below freezing, began to creep upward from 50 degrees Celsius to 48 degrees Celsius, from 48 cc's to 45 degrees. The change was glacial, literally, but it was happening. The tipping point, the moment when the freeze began to break, the moment when the system tipped back the other way, might have come at the equator. There, where the sun shines most directly, where the angle of incoming sunlight is steepest and delivers the most energy per square meter, where the sun passes directly overhead at noon and daylight lasts nearly 12 hours year-round. The ice might have been slightly thinner or slightly less reflective due to dust and volcanic ash that had fallen on it over millions of years, darkening it, lowering its albedo just a bit. And there, at the equator, after 50 million years of continuous freezing, the temperature finally rose above, just barely, just for a few hours on the hottest day, but it was enough. Ice began to melt, just a little at Che. First, a few puddles forming on the surface during the brightest days, water pooling in depression, reflecting the pale sun. By night, they would refreeze, the water turning back to ice as the temperature dropped. But the next day, they would melt again, and each time they melted, they absorbed a little more heat than the surrounding ice. This is the albedo feedback in reverse. The same mechanism that drove the freeze, now driving the thaw. Water is dark compared to ice. It absorbs 90% or more of the sunlight that hits it, while ice reflects 80–90%. So once the first patches of open water appeared, even small patches, even temporary ones, they absorbed more heat. That heat melted more ice around them. That created more open water, which absorbed more heat, which melted more ice. The process fed on itself, accelerating, amplifying, a positive feedback running in reverse. Within centuries, perhaps, the equatorial oceans were ice-free, at least in summer. A band of open water circling the globe, dark and liquid, soaking up sunlight. Within millennia, the ice had retreated to mid-latitudes, the boundary moving north and south as the melt accelerated. And then, with a speed that must have seemed catastrophic after millions of years of unchanging stillness, the ice collapsed, not everywhere at once, not uniformly, but in a cascade, a rush, an avalanche of melting. This is what geologists call the thaw, the deglaciation, the end of snowball Earth. And it was as dramatic, as violent, as transformative as the freeze had been, just compressed into a much shorter time span. Where the freeze had taken thousands of years, the thaw might have taken only hundreds or thousands. It was a planetary awakening, a world returning to life. Imagine standing on that same glacier we visited before, that ice sheet that had been solid and unchanging for 50 million years. For millions of years, it has been your only reality. The temperature has never risen above freezing. The sun has shone on endlessly white ice. The wind has blown endlessly across its surface, polishing it smooth in some places, carving it into ridges in others. The surface has been scoured and shaped, but it has never melted, never softened, never changed its fundamental state. It has seemed eternal, permanent, as much a feature of the universe as the stars themselves. But now, things are different, subtle at first, so subtle you might not notice if you weren't paying close attention. The air is warmer, not warm, not by any stretch, not comfortable, but less brutally cold. The wind, still strong, no longer cuts quite as deep. The sun, still pale, seems to have a bit more strength to it, a bit more warmth in its rays. And there is a sound you haven't heard in eon, a sound that has been absent from the world for longer than mountains have stood. The sound of water, liquid water, moving water. At first, it's just a trickle, barely audible over the wind, meltwater forming in small streams on the surface of the glacier, carving tiny channels in the ice, channels no wider than your finger. The water is crystal clear, pure, the purest water imaginable, untouched by life or sediment or dissolved minerals. It flows downward, following the slope of the glacier, pulled by gravity, pooling in depression before overflowing and continuing its journey. It's the first liquid water to flow on the surface in millions of years, and it's beautiful, mesmerizing, a small miracle. As the days pass, as the sun climbs higher, as the CO2 continues to trap more heat, sheet. The trickle becomes a stream, and then a river. The ice is melting faster now, the surface softening under the increasingly warm sun, becoming slushy, porous. More and more channels carve their way across the surface, merging, joining, creating a network of meltwater streams that grow wider and deeper with each passing day. Cracks appear in the ice, hairline fractures at first, then widening into crevasses, deep blue slashes in the white surface. Chunks of ice break away, calving off the glacier's edge and crashing into the valleys below with thunderous roars that echo for kilometers. The sound is like nothing heard in millions of years. The sound of a world breaking apart, transforming, waking up, and then it rained. For the first time in tens of millions of years, water evaporates from the newly opened ocean, rises into the atmosphere on currents of warm air, condenses into clouds, and falls back to earth as rain. Not gentle rain, not the soft drizzle of a spring morning or the light patter of an autumn shower. This is a deluge, a torrential downpour, a flood from the sky. The atmosphere is thick with water vapor, supercharged with moisture from millions of square kilometers of newly opened ocean evaporating rapidly in the heat. The clouds are dark and heavy, towering thunderheads that reach into the stratosphere. And from them pours rain like the world has never seen. Rain that falls in sheet, in curtain, in solid walls of water. The rain accelerates the melting dramatically. It warms the ice. Each drop, a tiny packet of heat delivered from the relatively warm atmosphere. It carves channels through it, cutting deep grooves, undermining it from above. It pools on the surface, forming lakes that grow and merge and overflow, cascading over the edges of glaciers in waterfalls that thunder and roar. Glaciers that took millions of years to build, accumulating layer by layer, snow compacting into ice, begin to collapse in centuries. Ice sheet fragment, their pieces drifting as massive icebergs in the newly liquid ocean, mountains of ice floating and slowly melting, leaving trails of cold, fresh water in their wake. The world is transforming, almost too fast to comprehend, faster than anything in human experience. If you could watch it in time-lapse, you would see the white globe turning blue and brown and green, the ice retreating toward the poles, the oceans opening, the continents emerging from beneath their frozen shroud. It's a planetary resurrection, a world coming back to life. But here's where things get strained, where the story takes an unexpected turn, because the atmosphere, remember, is not normal. It's not the atmosphere of today, not even the atmosphere of pre-snowball Earth. It's filled with carbon dioxide, absurdly high concentrations of it, levels that have been building for millions of years. And with such high levels of CO2, with the ice retreating and no longer reflecting sunlight, with dark ocean absorbing heat, the greenhouse effect is extreme, more powerful than at any other time in Earth's history. Earth doesn't just warm back to its pre-freeze climate. It doesn't return to the moderate temperatures that existed before the ice came. It overshoots. It swings from one extreme to another, from a frozen snowball to a hothouse, a searing greenhouse planet where temperatures soar to levels almost unimaginable. The climate swings violently. Ocean temperatures, which had been hovering just above freezing beneath the ice, might have risen to 40 or even 50 degrees Celsius in the tropics, far warmer than today's tropical seas, which average around 25-30 degrees C. That's hot enough to make swimming uncomfortable, hot enough to stress most marine life, hot enough to fundamentally change ocean chemistry. The equatorial regions would have been unbearably hot, the air thick and humid, heavy with moisture. Rain would have been intense and constant, day after day, week after week, perhaps for thousands of years, as the hypercharged water cycle worked frantically to redistribute all that heat, to move energy from the equator toward the poles, to find a new equilibrium. And this heat, this intense warmth, combined with abundant rain, drove weathering at an unprecedented rate. Rain, now falling abundantly for the first time in millions of years, washed over the rocks exposed by the retreating ice. And these weren't just any rock. They were fresh, unweathered, their surfaces newly exposed after being buried under ice for epochs. They were like virgin stone, never before touched by rain, their minerals locked in crystal structures that had never been chemically attacked. The acidic water, laden with CO2, fell on these rocks and reacted with them vigorously. The reaction was rapid, almost violent in geological terms. The water dissolved minerals from the rock, releasing calcium, magnesium, sodium, potassium, all the ions that plants and animals need, all the building blocks of shells and skeletons. Rivers carried enormous loads of dissolved material into the ocean, far more than flows into the sea today, orders of magnitude more. The rivers would have been cloudy with suspended particles, white with dissolved mineral, chemical soups flowing from land to sea, and in the ocean, all that dissolved mineral, all that calcium and carbonate, reacted with the CO2 dissolved in the water. The chemistry is simple but profound. Calcium ions plus carbonate ion equal calcium. Carbonate, limestone. With so much material available, with conditions so favorable, limestone began to precipitate rapidly out of the seawater, forming crystals that grew and settled to the seafloor, accumulating faster than at any other time in Earth's history. This limestone was deposited rapidly, forming thick layers called cap carbonate. The name is descriptive. They're carbonate, limestone, that cap the glacial deposits, sitting directly on top of them like icing on a cake. These distinctive layers are found on top of glacial deposits all over the world, in rocks that are now scattered across different continents but were once adjacent, part of the same ancient shoreline. They're one of the key pieces of evidence for Snowball Earth, a geological signature that marks the moment when the freeze ended and the rapid weathering began, a record of the planetary scale chemical reaction that locked away all that excess CO2 and brought the climate back toward equilibrium. The cap carbonates are strained. Unlike normal limestone, they formed too quickly to have been built by organisms. They contain unusual crystal structure, fan-shaped crystals, and other formations that suggest rapid precipitation from seawater supersaturated with dissolved mineral. They have strange isotopic signature, ratios of carbon-12 to carbon-13 that don't match normal limestone, evidence of the unusual chemistry during the thaw. They're distinctive, unmistakable, a fingerprint left by Snowball Earth. But this equilibration, this return to normal conditions, took time, not as long as the freeze, not millions of years, but thousands, perhaps tens of thousands of years. And during that time, Earth was a strange, hostile, transitional place. Too hot, too wet, too volatile, too chemically extreme. The oceans were warm and acidic. The atmosphere was thick and humid. Rain fell in torrents. Rivers carved deep valleys in the newly exposed rock. It was a world in flux, a world trying to find its balance, swinging wildly between extremes before finally settling down. And yet, paradoxically, it was during this chaotic transition that something remarkable happened, something that would change the future of the planet forever. Life, which had survived the freeze in small, isolated pockets, clinging to existence in hydrothermal vents and beneath the ice and in volcanic pools, began to spread again. As the oceans warmed and opened, as sunlight penetrated the water once more, for the first time in millions of years, photosynthesis resumed. Algae and cyanobacteria, dormant for so long, frozen or barely metabolizing in the darkness, came back to life. They woke from their long sleep. Their cells resumed their process. They began to photosynthesize, capturing sunlight, splitting water molecules, releasing oxygen, building sugars, growing, dividing, reproducing. They spread across the newly available habitat, colonizing the warming ocean, finding niches, exploiting opportunity. And they reproduced rapidly, explosively, bloom after bloom, turning the water green and then brown with their abundance, their populations expanding exponentially after being suppressed for so long. It was like a spring after the longest winter imaginable, life surging back with desperate energy, and the ice, the freeze and thaw, had changed things fundamentally. The climate had been so extreme, the conditions so unstable, that the freeze had acted like a massive evolutionary filter, a test that only the very hardiest organisms could pass. Complex organisms, if they had existed before the freeze, would have been wiped out. Specialist organisms, those adapted to narrow ranges of temperature or chemistry, would have died. Only the generalists survived, the tough ones, the flexible ones, the ones that could shut down and wait, and then restart when conditions improved. And those survivors, freed from competition when the thaw came, found themselves in a world of opportunity. Empty niches everywhere, abundant nutrients washing off the continent. No predators, because predators hadn't evolved yet. No competitors, because most lineages had been wiped out. It was a blank slate, an open field, a planet waiting to be colonized. Some scientists believe, and the evidence increasingly supports this idea, that this is why complex life appeared when it did. That Snowball Earth, as catastrophic as it was, as close as it came to ending life forever, actually paved the way for the evolution of animal, for the rise of complexity, for the explosion of diversity that would follow. The idea is controversial, debated, not universally accepted, but it's compelling. The hypothesis goes like this. The freeze itself acted as a bottleneck, a narrowing of the genetic pipeline. It wiped out many lineages, yes, but it also forced the survivors to adapt to extreme conditions. The genetic stress, the selective pressure, the mutations that accumulated during the long freeze might have driven innovations in cell structure, in metabolism, in the ability to tolerate environmental change. The survivors weren't just lucky, they were different, changed, carrying new genes, new abilities, new potential. And when the ice melted, the rapid weathering released enormous amounts of nutrients into the ocean. Nutrients that had been locked away in rock and sediment during the freeze. Phosphorus in particular is essential for life. It's a key component of DNA and RNA, the molecules that carry genetic information. It's a key component of ATP, the molecule that carries energy in cell. It's a key component of cell membrane. Without phosphorus, life as we know it can't. And during the freeze, phosphorus would have accumulated in rocks and sediment, locked away, unavailable. But during the thaw, it was washed into the ocean in a massive pulse, a flood of nutrients that fed the blooming algae and cyanobacteria. This nutrient boom would have fueled unprecedented growth, and all that photosynthesis would have produced oxygen, lots of it, increasing oxygen levels in the ocean and atmosphere. And higher oxygen levels are crucial for large, complex organisms. Oxygen allows for more efficient metabolism, for more powerful muscles, for larger bodies, for more active lifestyles. Before Snowball Earth, oxygen levels may have been too low to support anything more than small, simple organisms. After the thaw, oxygen rose, and suddenly new possibilities opened up. There's also the possibility that the freeze disrupted the existing ecosystems so thoroughly that it removed ecological barriers that had been holding life back. Before Snowball Earth, life was dominated by microbial mat, thick layers of bacteria and algae that covered the seafloor like living carpet, soaking up most of the available nutrients and light. These mats were incredibly successful, but they may have made it difficult for other forms of life to gain a foothold. Complex organisms might have struggled to compete against the efficiency and resilience of microbial mat. But the freeze could have broken up those mats, shattered them, reduced them to scattered remnants. And in the aftermath, when life returned, the mats didn't immediately reform to their previous dominant. There was open space, empty seafloor, opportunities for new strategy, new body plan, new ways of living. And into that space, evolution poured its creativity. Whatever the exact mechanism, and scientists are still working out the details, still running experiments and analyzing fossils and building models, the timing is suggestive, almost impossible to ignore. The Marinoan glaciation, the second and last of the major Snowball Earth events, ends around 635 million years ago. And within just a few million years, geologically an instant, a blink, the first large, complex organisms appear in the fossil record. These are the Ediacaran biota, named after the Ediacara Hills in South Australia, where they were first discovered in the 1940s, though they're now known from sites all over the world. And they were unlike anything alive today. So strange that when they were first found, scientists weren't sure what they were looking at. Were they animals, plants, fungi, lichens, something else entirely? A failed experiment in complexity that left no descendant. The Ediacaran creatures were soft-bodied, lacking shells or skeletons or any hard part. This makes them incredibly rare in the fossil record. Soft tissue almost never fossilized. It decays too quickly, is eaten too readily, leaves no trace. But in a few special places where burial was rapid and conditions just right, impressions of these organisms were preserved, pressed into the seafloor, mud like leaves pressed in a book. And that mud turned to stone, and those impressions endured. They came in a bewildering variety of forms, shapes that don't fit easily into modern categories. Some looked like quilted mattresses, oval or circular bodies with a pattern of ridges, and valleys lying flat on the seafloor. Were they animals that absorbed nutrients through their skin? Were they colonial organisms, many individuals living together in a structured mat? We don't know for sure. Others were tall and frond-like, anchored to the bottom by a holdfast and swaying in the current, reaching upward toward the light, filtering down from above. They looked like ferns or leaves, but they lived in the deep ocean where no plant could survive without sunlight. Were they animals filter feeding on particles in the water? Were they something else? A form of life that no longer exists? The mystery deepens the more we study them. Still others were disc-shaped, or ribbed, or segmented in ways that suggest bilateralism, the left-right symmetry that characterizes most modern animals. Some crawled across the seafloor, leaving tracks and trails that are preserved alongside their body fossils, evidence of movement, of behavior, of something approaching purpose. There was Dickinsonia, perhaps the most famous of the Ediacaran organism, an oval creature that could grow up to a meter long. Its body was ribbed, segmented, with a central groove running down its length. For decades, scientists debated what it was. Was it an early animal? Perhaps related to worms or flatworms? Was it a giant protist, a single-celled organism that had grown to enormous size? Was it a lichen, a symbiotic partnership between a fungus and algae? Recent chemical analysis of Dickinson fossils, looking at the types of fat molecules preserved in the rock, suggests it was indeed an animal, one of the earliest known, though exactly what kind remains unclear. There was Charnia, which looked like a fern frond, feather-shaped and delicate, anchored to the seafloor by a disc-like holdfast. It lived in deep water, below the reach of sunlight, so it couldn't have been photosynthetic. It must have been feeding on particles in the water, or perhaps on dissolved organic matter, a strategy used by some modern animals, but rare and unusual. There was Kimberella, which may have been an early mollusk, a slug-like creature that crawled across the seafloor, leaving trails behind it. Some fossils preserve what looks like a feeding trail, a scrape mark, where it might have been grazing on bacterial mats with a radula-like structure, a ribbon of tiny teeth like modern snails and slugs. If this interpretation is correct, Kimberella would be one of the earliest known bilaterians, animals with left-right symmetry, a head and a tail, a fundamental body plan that would give rise to most modern animals. There were dozens, perhaps hundreds, of other forms, many known from only a single specimen, others more common, but still mysterious. Flat disc, ribbed oval, branching frond, bizarre quilted structure. They represent a flowering of complexity, a sudden expansion in the size and diversity of life, an experiment in multicellularity on a scale the planet had never seen, and they appeared not long after. The world thawed, not long after the ice retreated and the oceans opened, and nutrients flooded into the sea, and oxygen began to rise. Coincidence? Perhaps, but many scientists think not. The connection seems too strong, the timing too perfect. Snowball Earth in, and within a few million years, complex life emerges. Cause and effect may be separated by a few million years, but in the vast sweep of Earth's history, that's nothing. That's direct. That's causal. The leading hypothesis is that the snowball Earth events, catastrophic as they were, created the conditions that favored the evolution of complex multicellular life. The freeze acted as a bottleneck, pruning the tree of life, wiping out many lineages and forcing survivors to innovate. The thaw released nutrients, flooded the oceans with phosphorus and other essential elements. The increased weathering, the warming climate, the disruption of microbial mats, all of it created opportunities for new forms, new strategies, new experiments in living. An evolution that blind, patient, relentless process seized those opportunities. It always does. Given time, given resources, given empty niches to fill, evolution produces diversity. It experiments. It tries new things. And some of those experiments work, survive, spread, become the ancestors of future lineages. The Ediacaran period, as fascinating as it was, as strange and beautiful as its organisms were, was just a prelude, just the opening act. The real explosion of animal diversity came later, in the Cambrian period, starting around 541 million years ago. This is the famous Cambrian explosion, one of the most dramatic events in the history of life, when most of the major animal phyla, the fundamental body plans that characterize modern animals, appeared in the fossil record in a geologically short span of time, perhaps just 10 or 20 million years. Suddenly, there were animals with hard shells made of calcium carbonate or silica, protective armor against predators and the element. There were animals with jointed legs that could walk and run and burrow. There were animals with compound eyes, complex organs that could form images, that could see the world in detail, that could track prey and avoid predators. There were predators and prey, a division that hadn't existed before, a new dynamic that would drive evolution forward in an arms race that continues to this day. There were burrowers that dug into the seafloor, mixing sediments, oxygenating the substrate, creating new habitats. There were swimmers that could move through the water column with purpose and speed. There were filter feeders that strained tiny particles from the water, exploiting a food source that had been there all along, but never efficiently harvested. There were scavengers that ate the dead, recycling nutrients, speeding up the flow of energy through ecosystems. The ecological complexity of the oceans increased dramatically, exponentially. The food webs grew longer and more, and tangled. An evolution, no longer constrained by the limits of soft-bodied simplicity, began to experiment wildly with form and function. Trilobites scuttled across the seafloor on their many jointed legs, their compound eyes scanning for food, their hard exoskeletons protecting them from the first predators. Anomalocaris, a meter-long predator, with grasping appendages and a circular mouth full of sharp plates, hunted in the water column. The apex predator of its time, a terror to other Cambrian creatures. Hallucigenia, a bizarre creature covered in spines with tentacle-like legs, walked awkwardly across the bottom. Its body plan so strange that scientists initially reconstructed it upside down. Opabinia, with its 5 eyes and long grasping proboscis, looks like something from an alien world. Wiwaxia, covered in scales and spines, grazed on bacterial mats. The diversity was staggering, overwhelming, a riot of forms and function. And it all happened relatively quickly, within 10 or 20 million years. Fast by geological standards, though still incredibly slow by human standards. It was as if evolution, held back for so long, suddenly broke free and ran wild, trying every possible variation, filling every possible niche, exploring every corner of morphological space. The connection between Snowball Earth and the Cambrian explosion is still being worked out, still being debated and refined. The two events are separated by about 90 million years, so the link is not direct, not immediate. But many scientists believe that Snowball Earth set the stage, created the precondition, established the foundation. It created high oxygen levels through the post-thaw algal blooms. It released nutrients through intense weathering. It wiped the slate clean of old ecosystems, making room for new ones. It created evolutionary pressure through extreme environmental stress. And once those conditions were in place, once oxygen was abundant and nutrients were flowing and ecological space was open, evolution took off. The Ediacaran organisms were the first experiment, the first tentative steps into complexity. Some of them may have been evolutionary dead-end, lineages that flourished for a time and then disappeared, leaving no descendant. But others may have given rise to the Cambrian animals, or at least to their immediate ancestors. The transition from soft-bodied Ediacaran forms to hard-shelled Cambrian animals remains one of the great mysteries of paleontology, but the pieces are slowly coming together, the story gradually being revealed through careful study of fossils and genes and development. So in a strange way, in a profound and unsettling way, the greatest catastrophe in Earth's history might also have been one of its greatest opportunities. The freeze that nearly ended life also, ultimately, paradoxically, allowed it to flourish in ways it never had before. The planet's darkest hour became, eventually, its brightest dawn. The longest winter gave way to the most vibrant spring, and life, tested to its absolute limits, proved not just that it could survive, but that it could emerge stronger, more complex, more diverse, more wonderful than ever. But Snowball Earth is not just a story from the deep past, not just an interesting chapter in Earth's ancient history. It has echoes that reach into the present, ripples that still move through our modern world, and it carries lessons, warning, insights that resonate today with urgent relevance. For one thing, it shows us just how sensitive Earth's climate can be, how delicate the balance is between the forces that warm and the forces that cool. The transition from a temperate planet to a frozen snowball, or from a snowball to a hothouse, can happen relatively quickly once certain thresholds are crossed. Not quickly in human terms, not overnight, or even within generations, but quickly on geological timescales, within thousands of years rather than millions. The ice albedo feedback is powerful, incredibly powerful, and once it gets going in either direction, once it tips past a critical point, it's extraordinarily hard to stop. It feeds on itself, amplifying, accelerating, running away. This has profound implications for understanding Earth's climate system today, for predicting how our planet will respond to the changes we're making. We're currently in an ice age, though you might not realize it from the weather outside your window. The presence of permanent ice at both poles, in Antarctica and the Arctic, defines an ice age, and we're living in what's called an interglacial period, a warmer phase within that ice age, a temporary thaw. Over the past 2 million years, Earth's climate has cycled between glacial periods, when ice sheets covered much of North America and Europe, and sea levels dropped more than 100 meters, and interglacials like the one we're in now, when the ice retreats and temperatures rise and the seas fill again. These cycles are driven by changes in Earth's orbit and axial tilt, patterns called Milankovitch cycle, after the Serbian mathematician who first calculated. The shape of Earth's orbit changes over time, stretching from nearly circular to slightly elliptical and back again over about 100,000 years. The tilt of Earth's axis wobbles between about 22 and 25 degrees over 41,000 years, and the direction that axis points, which determines which hemisphere gets more sunlight in summer, precesses like a spinning top over 26,000 years. These orbital changes alter how much sunlight different parts of Earth receive at different times of year, and those changes, though small, are enough to trigger the growth or retreat of ice sheet. But the orbital changes alone aren't enough to explain the magnitude of the glacial cycle. They're the trigger, but the ice albedo feedback is the amplifier. When orbital changes cause summers in the northern hemisphere to become slightly cooler, snow that falls in winter doesn't completely melt in summer. It accumulates. Over decades and centuries, it builds into glaciers, and those glaciers reflect more sunlight, cooling the planet further, allowing the glaciers to grow faster. The feedback amplifies the small orbital change into a massive climate shift. The same thing happens in reverse. When orbital changes make northern summers slightly warmer, ice melts, exposing darker land and ocean, which absorbs more sunlight, warming the planet further, melting more ice. Understanding how these feedbacks work, how sensitive they are, how quickly they can drive change, how much they amplify small perturbations, is crucial for predicting Earth's future climate, especially now as human activity adds greenhouse gases to the atmosphere at a rate unprecedented in recent geological history, perhaps unprecedented in all of Earth's history except during the most extreme volcanic event. We're running a planetary experiment, changing the composition of the atmosphere faster than it has changed in millions of years. And we need to understand how the system will respond, where the tipping points are, how fast change might occur. Snowball Earth teaches us that Earth's climate can exist in multiple stable states, that the planet can tip from one state to another, and that the transition can be rapid and dramatic. It teaches us that feedbacks can overpower other regulatory mechanisms, that systems can run away with themselves. And it teaches us to be humble, to recognize that we don't fully understand all the complexities, all the interaction, all the thresholds. The planet is more dynamic, more changeable, more surprising than we often assume. Snowball Earth also teaches us about resilience, about the stubborn persistence of life, about survival against impossible odds. Life survived the greatest freeze Earth has ever known. It survived tens of millions of years of darkness, cold, and isolation, conditions that would kill most modern organisms almost instantly. And not only did it survive, it came back stronger, more complex, more diverse, transformed by the crucible of the freeze into something new and extraordinary. This is not to say that extinction events aren't devastating, aren't tragic, aren't catastrophic. They are. Snowball Earth likely wiped out countless lineages, entire branches of the tree of life, species, and even whole groups of organisms that we'll never know about, because they left no fossils, no trace, no evidence of their existence, except perhaps a few scattered molecules or genetic fragments we haven't yet learned to read. The diversity that existed before the freeze was lost, gone forever, irreplaceable. Evolution doesn't rewind. Extinct species don't come back. But life as a whole, life as a planetary phenomenon, life as a process and a presence is remarkably resilient. Given enough time, given any viable refuges at all, given even the smallest population of survivors, it recovers, it adapts, it fills the empty spaces left by extinction. It experiments with new forms. It diversifies. This has happened over and over throughout Earth's history. After every mass extinction, the 5 big ones and the many smaller ones, life has bounced back. Sometimes it takes 1,000,000 years, sometimes 10 million, sometimes longer, but it happened. The tree of life, though pruned severely, though cut back to a few surviving branches, continues to grow. This resilience comes from life's diversity, from the fact that organisms occupy every possible niche, exploit every possible resource, survive in every possible environment. As long as some organisms survive, as long as there's genetic variation within those surviving populations, as long as there's ecological opportunity for new forms to emerge, evolution can work its patient magic. New species arise through mutation and selection. New adaptations emerge through the blind trial and error of reproduction. New ecosystems form as organisms interact in novel ways. The tree of life, though damaged, regenerates. Of course, this doesn't mean we should be complacent about the current biodiversity crisis, about the 6th mass extinction that many scientists believe we're currently witnessing and causing. The resilience of life operates on timescales of millions of years, on spans of time that are meaningless to human civilization. Human civilizations operate on timescales of decades and centuries. If we drive thousands or tens of thousands of species to extinction within the next few centuries, if we disrupt ecosystems faster than they can adapt, If we push the planet past tipping point, life will eventually recover. Given enough time, given millions of years, the biosphere will regenerate, diversify, fill the empty niches. But that recovery won't happen in any time frame meaningful to us or our descendants or their descendants for hundreds of generations. The world that emerges will be different, fundamentally and profoundly different, shaped by what we've lost and what survived. It will be a diminished world, at least from our perspective, missing the species we knew, missing the ecosystems we grew up with, missing the beauty and complexity we took for granted, and we, or our descendants, will have to live in that diminished world. We'll have to cope with its limitation. We'll have to adapt to its new reality, or perish along with the species we failed to protect. So the lesson of Snowball Earth's resilience is double-edged. Yes, life persists. Yes, the biosphere recovers. But the recovery is slow, measured in geological time, and the world that emerges is not the world that was lost. It's something new, something different, shaped by the catastrophe and by what survived it. And if we value the world we know, if we want our descendants to inherit a planet that resembles the one we grew up on, then we have a responsibility to protect it, to preserve what we can, to avoid pushing systems past their breaking point. Snowball Earth also reminds us that Earth's story is not a simple progression from simple to complex, from bad to good, from primitive to advanced. It's not a story of steady improvement or linear development. It's a story of cycles, of ups and downs, of catastrophes and recoveries, of extinctions and radiation. The planet swings between extremes, though usually not as extreme as Snowball Earth. Ice ages and warm periods, high oxygen and low oxygen, supercontinents and scattered fragments. Nothing stays the same for long, at least not on geological timescales. Change is the only constant, and yet, through all these changes, through all these swings and cycles and catastrophes, certain patterns persist, certain systems endure. The water cycle, that endless movement of water between ocean and atmosphere and land and back again, has been operating for billions of years. The carbon cycle, that slow circulation of carbon between rock and ocean and atmosphere and life, has regulated the planet's temperature for eons. The rock cycle, that patient transformation of stone from igneous to sedimentary to metamorphic and back again, has been building and destroying mountains since the crust first formed. These are the planet's heartbeat, its breath, its metabolism. They operate on timescales far longer than any individual life, longer than species, longer even than most geological features. But they endure, and understanding them helps us understand not just the past, but the present and future as well. There's something humbling about contemplating Snowball Earth, something that puts our own lives, our own struggles, our own concerns into a larger perspective. We worry about the changing season, about a cold winter or a hot summer, about rain that comes too early or too late. But Earth has known winters that lasted 50 million years, summers so hot the oceans nearly boiled. We build cities and monuments meant to last centuries, structures we hope will endure long after we're gone, testaments to our civilization. But Earth has seen ice sheets kilometers thick rise and fall, has seen continents drift across the globe and collide and break apart, has seen mountains rise from plain and erode back to dust, all on timescale that make our greatest cities look like sandcasts high tide, here for a moment and then swept away. And yet, paradoxically, we're part of this story. We're not separate from it, not outside observers looking in. We're participants, active agents, characters in the ongoing narrative. We're descendants of the organisms that survived Snowball Earth, carriers of DNA that has been passed down, modified, refined over hundreds of millions of years. The DNA in our cells contains information that survived the freeze, that endured the darkness, that waited out the cold in some tiny refuge, and then spread again when the ice melted. We carry that history in every cell, that testimony to survival, that proof that persistence matters, the biochemistry that keeps us alive, the fundamental processes of metabolism and respiration and cell division. All of it was perfected in those ancient oceans, tested by the freeze, refined through countless generations of survivors. When you breathe, you're using oxygen produced by photosynthetic organisms whose ancestors survived Snowball Earth, whose lineage stretches back through that terrible freeze to the warm seas before it. When you drink water, you're consuming molecules that may have been locked in ice for millions of years during the freeze, that may have fallen as snow on a glacier 700 million years ago, and only recently melted and made their way through rivers and lakes to your glass. When you look at at the rocks beneath your feet. Some of them may contain dropstone, pebbles carried by glaciers to the tropics during snowball Earth and deposited when the ice melted. Foreign rocks in strange places. Evidence of a time when the impossible became real. The past is not gone, not truly. It's here, woven into the fabric of the present, written in stone and ice and the genes of every living thing. The story of Snowball Earth is our story too, part of the long chain of events and transformation that led to us, that made us possible, that shaped the world we inhabit. So what does the rock record actually tell us about Snowball Earth? How do we know this happened? How can we be so confident about events that occurred hundreds of millions of years ago, long before there were any witnesses, any observers, any record keepers? The evidence is scattered across the globe, preserved in formations that date to the Neoproterozoic era, and it comes in several forms, each piece contributing to the puzzle, each clue pointing to the same astonishing conclusion. First, there are the glacial deposits themselves, the rocks that were clearly formed by glaciers that bear the unmistakable marks of ice. In many places around the world, from Namibia to Australia, to Canada, to China, geologists have found layers of rock that contain the distinctive signatures of glacial activity. These include tillite, a type of sedimentary rock formed from glacial till, the unsorted mixture of clay, sand, pebbles, and boulders that glaciers grind up and carry with them as they flow. Till is distinctive because of this lack of sorting. When water deposits sediment, whether in a river or lake or ocean, it sorts the particles by size. Coarse material settles first, fine material last, creating layers. But glaciers dump everything together, fine clay and huge boulders all mixed up. And when that material is buried and compressed and turns to rock, you get tillite, a chaotic mixture frozen in stone. What makes these Neoproterozoic tillites remarkable? What makes them evidence for Snowball Earth, rather than just evidence for glaciers, is where they're found. They're not just at high latitude, where you'd expect ancient glaciers to have existed, where ice sheets form today in places like Antarctica and Greenland. They're found in rock that, based on paleomagnetic data, were at or near the equator when they formed. Paleomagnetic data comes from studying the orientation of magnetic minerals in rocks. When lava cools or when sediment settles, tiny magnetic crystals align with Earth's magnetic field, like tiny compass needles pointing toward the magnetic poles. That alignment gets locked in as the rock solidifies, and by measuring the orientation of those frozen compasses, geologists can determine the rock's latitude at the time of formation, can tell whether it was near the equator or the poles or somewhere in between. Finding glacial deposits at the equator is extraordinary, shocking, almost unbelievable. Today, glaciers are confined to polar regions and high mountains. The equator is the warmest part of the planet, the place that receives the most direct sunlight year-round, the place where ice should never form under normal circumstances. But during Snowball Earth, ice reached the tropics, covered the equator, turned the warmest regions of the planet into frozen wastelands. That's evidence of a truly global freeze, of conditions so extreme they defy our normal understanding of climate. Another striking piece of evidence comes from dropstone, also called ice-rafted debris. These are individual rock, often quite large, sometimes the size of your fist, or even bigger, found in the middle of fine-grained sedimentary layers that clearly formed in deep, quiet water far from shore. The fine sediment, thin layers of clay and silt, settled slowly out of the water column over long periods, layer by layer, each one representing years or decades of gentle accumulation. The particles are tiny, microscopic, carried far from shore by currents, and settling like dust through still water. But the large rock doesn't fit. It's too big, too heavy to have been carried by the gentle currents that deposited the surrounding sediment. It's out of place, anomalous, impossible to explain by normal sedimentary processes. The explanation is ice. The rock was frozen into a glacier or an iceberg, picked up on land, and carried out to sea. When the ice melted, or when the iceberg drifted out over the ocean and eventually melted, the rock dropped straight down to the seafloor, landing in the soft mud like a stone dropping into fresh snow. It punched through the fine sediment layers, sank partway in, and was then buried by more layers of fine sediment falling from above. Dropstones are smoking gun evidence of ice-covered ocean, of icebergs floating in open water, or of ice sheets extending over the continental shelves and into the deep sea. And like the tillites, they're found in rocks that formed at tropical latitude, at the equator, where icebergs shouldn't exist under normal conditions. Then, there are the cap carbonate, perhaps the most distinctive and dramatic evidence of all. These are thick layers of limestone, sometimes tens of meters thick, that sit directly on top of the glacial deposit. Remarkable abruptness. The transition is sharp, dramatic, often with no intermediate layers, no gradual transition. One moment, geologically speaking, there are glacial rocks, tillites and dropstones, evidence of ice. The next moment, there's limestone, massive amounts of it, thick beds of calcium carbonate. It's like flipping a switch, like turning a page from one chapter to another. This is strange, deeply strange, because limestone typically forms slowly over millions of years as organisms in the ocean, corals and shellfish and microscopic plankton, build shells and skeletons out of calcium carbonate, die, and settle to the seafloor. Their remains accumulate gradually, layer by layer, millimeter by millimeter, building up over vast periods of time. But the cap carbonates are different. They formed quickly, rapidly, on timescales of thousands to tens of thousands of years, rather than millions, and they contain unusual features, strange crystal structures, and textures that suggest rapid precipitation from seawater supersaturated with dissolved minerals. The crystals in cap carbonates are often fan-shaped or radiating, growing outward from nucleation point, forming structures that only occur when minerals precipitate rapidly from solution. The isotopic signatures are unusual too. The ratios of carbon-12 to carbon-13 and oxygen-16 to oxygen-18 don't match normal limestone, evidence of the unusual chemistry during the thaw, of the rapid weathering and extreme greenhouse conditions. Some cap carbonates contain features called crystal fan and sheet cracks, structures that form when sediment dries out and then gets wet again, evidence of sea level fluctuations and possibly extreme conditions right at the transition from freeze to thaw. The explanation, the reason these cap carbonates formed so rapidly and so universally, ties directly back to the thaw we discussed earlier. When snowball Earth ended, when the ice melted and temperatures soared, when the extreme greenhouse kicked in, weathering went into overdrive. Rain fell torrentially on rocks that had been fresh and unweathered, protected under ice for millions of years. The chemical reactions were rapid, violent almost. Enormous amounts of calcium and other minerals dissolved and washed into the ocean in a massive pulse. And in the ocean, supersaturated with dissolved ion, limestone began to precipitate rapidly out of the water, coating the seafloor in a thick chemical blanket. The cap carbonates are the signature of that chemical storm, the mark left by the transition from icehouse to hothouse, a testament to how extreme the conditions were during the thaw. There are also the banded iron formations, or BIFs, that appear during some snowball Earth interval, though not all. BIFs are distinctive rock with alternating layers of iron-rich and iron-poor sediment, usually red and black or red and gray, creating a striped appearance. They're composed primarily of iron oxides and silica, and they form in unusual conditions that don't exist on Earth today. Specifically, they form in oceans where dissolved iron is abundant, but oxygen is scarce. Here's how it works. Iron dissolves easily in oxygen-free water, but as soon as oxygen is present, it reacts and precipitates out as iron oxide, rust. So in an oxygen-rich ocean like today, iron doesn't stay dissolved. It rusts and sinks almost immediately. But in an oxygen-poor ocean, iron can accumulate in the water, building up to high concentrations over time. Then, if oxygen is introduced periodically, perhaps seasonally, or through pulses of photosynthetic activity, the iron precipitates out in bursts, settling to the seafloor in layers. BEFs were common in Earth's early history, before the Great Oxygenation Event around 2.4 billion years ago, when the oceans were largely anoxic and iron could accumulate. But they largely disappeared after oxygen levels rose in the atmosphere and ocean. Their reappearance during snowball Earth intervals is therefore significant, evidence that the oceans became anoxic again, depleted of oxygen, returned to a state they hadn't experienced in over 1 billion years. This makes sense in the context of snowball Earth. With the ocean frozen over, sealed beneath ice, cut off from the atmosphere, oxygen couldn't enter from above, and with photosynthesis reduced to near zero, no oxygen was being produced in the water. The deep ocean would have become anoxic, oxygen depleted, and iron dissolved from volcanic vents and weathered rocks would have accumulated over millions of years. Then, when the thaw began, when photosynthesis restarted and oxygen began to return, the iron would have precipitated out rapidly, creating banded iron formation. It's another piece of evidence, another clue, another way the rocks tell us the story of snowball Earth. All of these lines of evidence, glacial deposits at the equator, dropstones in tropical seas, cap carbonates marking rapid chemical change, banded iron formations suggesting anoxic ocean, they all paint a consistent picture. They all point to the same conclusion. Earth froze, completely or nearly completely. Ice reached from pole to pole, from the highest mountains to the lowest valley, from the continent to the ocean floor. And then it thawed rapidly and dramatically in a planetary scale chemical reaction that left its signature in limestone beds around the world. But the debate isn't entirely settled, isn't completely resolved. Science rarely is. Some scientists argue for a slush ball Earth rather than a complete hard snowball. In this model, the planet was mostly frozen, covered in ice over most of its surface, but a belt of thin ice, or even open water, persisted near the equator. This would have allowed photosynthesis to continue at a minimal level, maintaining some oxygen production, providing a refuge for more complex life than could survive in total darkness beneath thick ice, avoiding some of the more extreme consequences of a complete freeze. The evidence is actually compatible with both scenarios, with both hard snowball and slush ball, and the truth may have varied between the different glaciation events. The Sturtian might have been a harder freeze than the Marinoan, more complete, more severe. Or conditions might have fluctuated over the tens of millions of years each event lasted, with periods of harder freeze alternating with periods of partial thaw, the planet cycling between snowball and slushball state. The debate continues as scientists refine their models, discover new evidence, develop new techniques for extracting information from ancient rock. That's how science works, not through pronouncements of absolute certainty, but through gradual refinement, through accumulation of evidence, through testing of hypotheses, through debate and discussion and the slow approach toward truth. But whether it was a true hard snowball or a slush ball, whether the freeze was absolutely complete or merely nearly complete, the basic story remains the same, the fundamental narrative unchanged. Earth experienced the most extreme climate events in its history, perhaps the most extreme climate events possible for a planet with liquid water. Ice covered most or all of the surface. Life was pushed to the absolute brink of extinction. Survival became a matter of waiting in darkness and cold for millions of years. And yet, incredibly, miraculous, life did survive. And when the ice finally melted, when warmth and light returned, life roared back, exploding into new form, new sizes, new complexity, transformed by the ordeal into something richer and stranger and more wonderful. Let's return one final time to the ice, not to understand the science, but to feel it, to experience, to let it sink into our bones, to imagine what it would have been like to exist in that world. If somehow you could stand as a witness to that frozen planet and comprehend what you were seeing. You're standing on the frozen ocean, far from any coast, thousands of kilometers from the nearest land. You've walked for months across the ice, though in truth, there's no way to measure time here, no way to mark the passing of days except by the rising and setting of that dim, distant sun. The ice beneath your feet stretches in every direction to the horizon and beyond, an endless plain of white, unbroken, featureless, except for the wind-carved ridges and the occasional pressure crack where the ice has buckled under its own weight. This ice is thick beyond comprehension, a solid lid kilometers deep pressed down on the ocean below. It has been here for millions of years, accumulating layer by layer, each year's snowfall adding another thin increment, compacting under its own weight into this massive frozen barrier. The surface is ancient. The top layer you're standing on might have fallen as snow 10,000 years ago, or 100,000, or longer. Time has no meaning here. There are no trees to count rings in, no sediment layers to measure, no fossils to mark the passage of epoch. There is only the ice, and it has always been, and it seems as though it will always be. The horizon stretches in every direction, flat and white and endless. There are no landmarks, no features to guide you, no way to know if you've been walking in circles or in straight line. The ice all looks the same, sculpted by wind into the same pattern, the same ridges, the same texture. You could walk for a lifetime and never reach the edge, never find anything different, never escape this frozen prison. The sky is pale, washed out, the color bleached by the endless reflection from below. The sun, when it's visible, is a dim disk struggling to break through the ice crystals suspended in the air, halo surrounded, distant, cold, offering no warmth, no comfort, no hope. At night, the stars wheel overhead in their ancient pattern, brilliant and clear. So many of them that they seem to merge into a glowing river across the sky. You can see galaxies, nebulae, cosmic clouds, details invisible from modern Earth with its light-polluted sky. The universe is laid bare, beautiful and terrible in its vastness, and you are alone beneath it on a frozen world, and beneath your feet, beneath the ice, beneath kilometers of frozen water, is the ocean. You know it's there, even though you can't see it, can't hear it, can't feel it. Down there in the darkness, in the cold, cut off from the sun and in the sky, and the cycles that once sustained it, the ocean wait. It's still liquid, kept from freezing by the salt dissolved and by the pressure of the ice above. But it's dark, completely dark, darker than any cave, darker than the deepest mine. No light has penetrated in millions of years. No photon from the sun has reached that water since the ice closed over it like a coffin lid. And in that darkness, in that cold, in that stillness, life waits too. Bacteria clinging to rocks around hydrothermal vents deep on the ocean floor. Their metabolism slowed to almost nothing, barely alive, barely maintaining themselves, just waiting. Algae frozen in the ice, their cells dormant, their chlorophyll still intact, but useless in the dark, waiting. Spores drifting in the frozen ocean, suspended in time, neither alive nor dead, but somewhere in between, waiting. They've been waiting for millions of years, and they'll wait for millions more, if necessary. They have no choice, no volition, no awareness. Time pass. They simply endure, persist, hold on to existence by the thinnest thread. They are life at its most minimal, its most stubborn. They are proof that life, once it begins, does not easily, that given any chance at all, any refuge however small, any possibility however remote, life will cling on. Days, weeks, years, centuries, millennia, and nothing changes. The ice remains, the cold remains, the darkness remains. Time loses meaning. When nothing ever changes, when each day is identical to the one before and the one after, the sun rises and sets, billions of times. The moon orbits, pulling invisible tides beneath the ice. The stars wheel overhead in their patient dance. But on the surface, nothing moves, nothing grows, nothing lives. It is a world in stasis, frozen not just in ice, but in time itself, waiting for something, anything, to break the spell. And then, after 50 million years, after an expanse of time so vast it makes human history look like the blink of an eye, something shifts. The temperature rises, just a fraction of a degree at first. Not enough to melt the ice, not nearly, not yet, but enough to notice. If anyone were there to notice, if anyone could somehow measure the tiny change. The sun seems slightly brighter, the wind slightly less bitter, and at the equator, where the sun shines most directly, a puddle forms, just a puddle. A few meters across, a few centimeters deep, liquid water on the surface of the ice for the first time in millions of years. And that puddle, tiny and insignificant as it seems, changes everything. It absorbs sunlight instead of reflecting it. It warms. The ice around it melts. The puddle grows. More water, more absorption, more warming, more melting. The feedback loop has reversed. And now, instead of cold, feeding more cold, warmth feeds more warmth. The process accelerates. Within years, the puddle becomes a lake. Within decades, a sea. Within centuries, the equatorial ice is gone. Open water encircling the globe, dark and liquid and warm. And then comes the rain. The first rain in 50 million years. The first time water has fallen from the sky since before the freeze began. It falls in torrent, in flood, in walls of water that seem to have no end. The atmosphere, thick with CO2, supercharged with greenhouse heat, pours out its moisture in a deluge that will last for thousands of years. Thunder echoes across the thawing landscape. Lightning splits the sky. The world shakes itself awake with violence and noise and motion after millennia of silence and stillness. Meltwater pours off the continent. Glaciers collapse. Ice sheets fracture. The world is transforming so fast that if you could watch it in time-lapse, if you could compress the centuries into seconds, you would see the white planet turning blue and brown before your eyes. The ice vanishing like frost in morning sunlight. The oceans filling. The land emerging from beneath its frozen shroud. And beneath it all, in the warming ocean, in the returning light, life stirs. Cells wake from dormancy. Metabolism restarts. Photosynthesis begins again. Algae bloom, turning the water green. Bacteria multiply, their populations exploding after being held in check for so long. Nutrients flood into the ocean from the weathering continent, feeding the bloom, sustaining it, amplifying. The ocean comes alive again after millions of years of death-like stillness. This is the promise that emerges from the catastrophe, the hope that rises from despair, that endings can be beginning, that from the deepest cold can come the most vibrant life, that patience and endurance, even over unimaginable spans of time, are rewarded, that nothing, no matter how terrible, no matter how total, lasts forever. That change, which can destroy, can also renew, that the longest winter eventually gives way to spring, and as that spring arrives, as warmth spreads across the planet, as ice retreats and oceans fill and life blooms and spreads, the world becomes something new. Not the world that existed before the freeze, not a restoration or a return, but a transformation, a planet reborn, a biosphere reinvented. And from that reinvention, from that crucible of ice and time, will eventually emerge eyes that can see, brains that can think, voices that can speak, hands that can shape stone, and build cities, and create art, and ask questions about where it all came from. We are, in the end, children of Snowball Earth, descendants of the survivors, carriers of the genes that endured the freeze. And in our DNA, in our cells, in the very structure of our body, we carry evidence of that survival, proof that our ancestor, our distant microbial ancestor, refused to give up, refused to let the cold be the end. Sleep well, child of the thaw. Dream of patience and endurance. Dream of darkness giving way to light. Dream of ice melting into ocean. Dream of life returning after the longest wait imaginable. And know that you are part of that story, part of the line that never broke, part of the life that refused to stop. From all of us at Earth's history, thank you for joining this journey into deep time, into deep cold, into the heart of one of the planet's greatest mysteries and greatest triumph. If this brought you peace, if it helped you see the world differently, please share it with someone else who might need it. And if there are other chapters of Earth's story you'd like to explore, other moments of transformation or resilience, leave your thoughts in the comments below. Until next time, rest well. The ice is gone, the world is warm, and life, against all odds, continues. Good night.